So good morning to all. So today we will start the session now. So in the previous session, so we have discussed about SR latch using NAND gates. Okay. Then we have discussed about flip-flops and what are the difference between latches and flip-flops, right? There is comparison of latches and flip-flops. And then we have discussed level triggered flip-flops, edge triggered flip-flops. Okay, so in this topic we have discussed what is meant by level, what is meant by edge. Okay, and then what is meant by level triggered flip-flops, edge triggered flip-flops. Then what are the further classification under these two categories. Okay, these things are discussed in this topic, right? Then we have seen what are the possible types of flip-flops. Okay, so basically we have 4 different types of flip-flops. SR flip-flop, D flip-flop, JK flip-flop, and T flip-flop. Okay, so among these 4 flip-flops, we have discussed about SR type flip-flop. Okay, so under this topic, we have discussed the schematic diagram for SR flip-flop, the logic table, so which describes the actual functionality of the SR flip-flop. Okay, and then we have discussed characteristic and excitation tables. Okay, so these things are discussed in the last session. Okay, so in this session we will start with the second type of flip-flop called D flip-flop, or you can say data flip-flop. Okay, so data flip-flop. So the first letter D represents the occurrence. Okay, so D flip-flop. So we will start with D flip-flop. So D stands for data, right? So D latch with enable pin. Okay, so actually we are constructing the flip-flop using latch element. Okay, so here also we are using D type latch. Okay, but we are dealing with flip-flop circuit. Okay, flip-flop means controlled or gated latch. Okay, so that controlling mechanism may be in terms of enable or clock pulse. Okay, so here D latch with enable input is called as level triggered D flip-flop, or simply you can say D flip-flop or data flip-flop. Okay, so D stands for data. So what is the purpose of the second type of flip-flop, that is D flip-flop? Okay, why we going to go for another type of flip-flop? Okay, so as seen in the SR flip-flop, for the combination S equal to 1 and R equal to 1. Okay, when you are applying S equal to 1 and R equal to 1, for this input combination, SR flip-flop produces invalid output. Okay, both Q and Q bar will be logic bar. That is not allowed in the flip-flop. Okay, so to avoid that invalid condition or indeterminate state of the SR flip-flop. Okay, so we are going for D type flip-flop, right? So here we will use a complementary input signals. Okay, so to avoid the 1 1, okay, S equal to 1 and R equal to 1, we are going to provide complementary inputs to S and R. Okay, that is D flip-flop stands for data flip-flop that eliminates the undesirable condition of the indeterminate state in the SR flip-flop by ensuring that the input S and R are never equal to 1 at the same time. Okay, so the D input directly goes to S input and its complementary form is applied to R input, right? So this is the schematic of D flip-flop. Okay, so same structure as used in the SR flip-flop, but the difference is here we are applying only one input instead of 2. S and R, we are only applying single input, that is D. Okay, that D is again complemented, okay, for second input. So in this diagram you can observe that if you are recalling the SR flip-flop, so this is our S input, this is our R input. Okay, with a control signal, that is enable or clock pulse. Okay, but here we are designing D flip-flop. Okay, so in this D type flip-flop, we are giving data input directly to input signal yes. Okay, and then complemented of D is given to the input signal R. Okay, so this whole structure is nothing but D flip-flop. Okay, once again it is derived from SR flip-flop structure. Okay, so this is the logic diagram for data flip-flop or simply D flip-flop. Okay, so this is the a logic table or functional table for D type flip-flop. Okay, so here in this diagram we can observe that D is the input signal, C is the control signal. It may be enable or clock pulse. Okay. Okay. So now assume that the outputs of D flip-flop, Q and Q bar. So I'm assuming as Q equal to 1, Q bar equal to 0. Okay. So this is for assumption to understand the function of this D flip-flop. Okay. So now the first possibility is when I am disabling the clock pulse or enable signal. Okay, and disabling the enable signal. What will happen? Both NAND gates 1 and 2 or for example 3, 4. This is NAND gate 1 and 2. Okay, so that NAND gates 3 and 4 receives 0. If any one of the input is 0, obviously we know that the output of NAND gate is logic 1. Okay. If the inputs applied for this SR latch, okay, so this is the SR latch. The input for this SR latch is 1, 1, right? Then what about the output of or the state of this SR latch? No change state. Okay, that is memory state. Or you can also observe the output produced by this circuit. Okay, so here the output available is 1, here also 1. Okay, previously assumed the outputs are Q equal to 1, Q bar equal to 0. Okay, so for NAND gate 1, this input, the Q bar is fed back and this NAND gate 1 receives logic 0 at the 1 input. Okay, so one of the input is 0, obviously this NAND gate 1 produces logic 1. Okay, logic 1. Okay, then the same Q will be applied to NAND gate 2. Again, the output coming from NAND gate 4 is 1. So this NAND gate gets 1 on both the input lines. Okay, so obviously this NAND gate 2 produces logic 0. Right? So it maintains the previous state outputs. 1 at the Q, 0 at the Q bar. It is maintained. So there is no change in the previous state outputs, right? So this type of operation is nothing but memory state. Okay, so that is the listed in the table. Okay, whenever the clock pulse or control signal is 0, irrespective of the input signal that is applied D input, okay, the output of D flip-flop does not change. Okay, it goes to memory state, right? So now the second case, if I am applying the input signal, I am enabling the input signal. Sorry, I am enabling the clock signal. Okay, I am enabling the clock signal by applying logic 1, right? Then, if I am applying logic 0 at the data input, okay, so now the D having value 0, C the control or clock signal having logic 1. Okay, so what happened for this input combination? Okay. So assume that the previous state outputs are 1 and 0. Okay, Q equal to 1, Q bar is equal to 0. Okay, so here I am enabling the clock pulse or control signal with the logic 1, and I am applying data input as logic 0. Okay, so this line is having the NAND gate 3 having 0 on one input, 1 on another input. Okay, which is coming from clock signal or control signal. Okay, similarly, the NAND gate 4 having logic 1 in first input. On second input, this 0 is complemented using this inverter or NOT gate. Okay, so the second input of NAND gate 4 is also logic 1. Okay, so both the inputs for NAND gate 4 is 1. So the output of NAND gate 4 is 0. Right? What about output of NAND gate 3? Here the one of the input is logic 0. So output of NAND gate 3 is logic 1. Right? Again. So here the S bar is 1. If S bar is 1 means what? R bar is equal to 0. Okay. The true form enna S bar 1 na S value 0. Right? S value 0, R value 1. Okay. If R value is 1, that means that reset condition. Okay. So what will happen? The Q goes to 0. Okay, Q bar goes to 1. Right? Or otherwise, you can observe the operation of whole circuit based on this signal generated in the circuit. Okay, so S bar having logic 1, R bar having logic 0. Okay, now the 1 is applied to one of the input of NAND gate 1. The another input is coming from Q bar. Previously we are assuming that 0. Okay, now R bar is equal to 0. Okay, this R bar is equal to 0. This signal is applied to NAND gate 2. Right? So NAND gate 2 having one input as logic 0. The another input coming from Q. Okay, Q is 0. Sorry, Q is 1. That 1 is applied to NAND gate 2. Okay, so now 1, 0. So obviously this NAND gate produces logic 1. Again, this logic 1 is applied to NAND gate 1. Okay, so S bar is 1. Q bar is also 1. So 1, 1 produces logic 0. Right? So Q goes to 0 from logic 1. Q bar goes to logic 1 from logic 0. Okay, now output is 0. Okay, Q is 0. If the output Q is 0, then that particular condition is known as reset condition. Similarly, if you are applying logic 1, okay, when I am applying input 1 at the data line, okay, what will happen? The output will be 1. Okay, how? You can observe the operation. So here so we will take 0 as the previous state, 1 as the Q bar previous state values. Okay, so by assuming these kind of values, I am applying logic 1 on the D line and enabling control signal C. Okay, so now these two inputs are 1 and this is also 1. Then due to NOT gate, this line goes to 0. Okay, so now 1, 1 produces 0 on the S bar, 1, 0 produces logic 1 on the R bar. Okay, so now here 0, here 1, right? So the Q bar, previous value of this Q bar is 0, that 0 is applied to NAND gate 2. Okay, so 0, 1 produces 1. And again this 1 is applied to here. 0, 1 produces logic 1. This logic 1 is applied here. Sorry. So it goes to 0. Right? So I'm repeating. So for the input D equal to 1, okay. So NAND gate 3 having logic 1 on both the inputs. So NAND gate 3 produces logic 0. Okay. Similarly, NAND gate 4 produces logic 1 because one input having logic 1, another input having logic 0. Okay. Then this 0 S bar is applied to NAND gate 1. Right? So the Q bar, the previous value of Q bar is assumed as logic 1. This logic 1 is applied to NAND gate 1. So here NAND gate 1 having logic 1 on one input, logic 0 on the another input. So this NAND gate produces logic 1 here. Okay. Then again this logic 1 is applied to NAND gate 2. This NAND gate 2 having logic 1 on both the inputs. So this NAND gate 2 produces logic 0 at the output. That is Q bar. Okay. Now for this input combination, Q goes to logic 1. That is set condition. Right? So hope you all understand the operation of D flip-flop. Right? Any doubt? Do you have any doubt? Post it in the chat box. Otherwise, I can continue. Any doubt? Okay. No doubts. Sabhi City saying no, no sir. Okay, I'm continuing. So this is the example for understanding the operation of D flip-flop in terms of waveforms. Okay. So here, here we are taking waveforms. Okay. Here in the circuit, I put logic 1, logic 0. Okay. In terms of values, we have understand the operation. Okay. Same thing is graphically depicted here. Okay. So C represents clock signal or control signal. Okay. So here initially we are assuming 0 and then it goes to logic 1 and then it goes to logic 0. Okay. 0, 1, 0. Right? 0, 1, 0. Okay. So whenever the clock signal or control signal C is enabled, then only the D flip-flop produces output Q. Okay. When clock signal or control signal is 0, that is disabled, then output of D flip-flop does not change. Okay. It goes to memory state or it maintains the previous state values. Okay. That is the thing observed from this operation of D flip-flop. Okay. That can be also understood from this timing value. Right? So I'm taking a clock signal or control signal like this and I'm applying data input like this. Okay. Then for these two signals, what will be the output Q? Right? So here the Q will be produced like this. So you can observe the waveforms. Initially, clock is 0, data input D is also 0. Okay. So previous value of Q is assumed as 0. Right? So because of clock input 0, Q also maintains logic 0 because we are assuming that Q was 0 previously. Right? Now, data input D is changing at this time. At this time, data D is changing. Okay, but clock is still disabled. Right? So what will happen? Q does not change. Okay, Q does not change, it maintains previous value. So it maintains previous value up to the clock is enabled. Okay, when the clock is enabled, that is switched from 0 to logic 1. Okay, then Q follows the input D. Right? When clock is enabled, then Q gets the value of D. So now D is logic 1. That logic 1 is applied to output Q. Okay, so it maintains up to this time, because up to this time only D having logic 1. Okay, then D goes to logic 0. Okay, for this changes, Q also changes to logic 0 because clock is enabled still. Okay, clock having logic 1. Okay, so if clock is logic 1, whatever may be the change in data input, that will be reflected in the output Q. Okay, so when clock is 1, if D is logic 1, Q is also logic 1. If D is logic 0, then Q also goes to logic 0. Then D changes from 0 to logic 1, right? So Q also changes from 0 to logic 1. Okay, so up to this time. And then listen, up to this time, clock is logic 1. After that, clock is disabled. Okay, clock goes to logic 0. Okay, if the clock is disabled, what will happen? Irrespective, whatever may be the data in input line, that is the value of D, Q does not care about that. Okay, it maintains previous state values. Okay, so up to this time, Q is logic 1. If the clock is disabled, then Q maintains previous state value. So here also you can observe that logic 1. Okay, so even though D goes to logic 0, it maintains still logic 1. Okay, that is, it goes to memory state. So after this time, it goes to memory state. Right? Hope you all understand this timing diagram. Is it right? Okay. So this is the another example for understanding the D flip-flop. So here we are having continuous clock signal. Okay, three clock pulses. Okay, so among these 3 clock pulses, we are applying input D. Okay, and then we are going to observe the output Q. Right? Listen here, that clock is 0 up to this time. Okay, so output Q also maintains previous state value. If you are assuming the previous state value is logic 0, then Q maintains logic 0 up to this time, because clock is disabled. That is, clock is 0. Okay, when clock is 0, even though the data is varying, that will not be reflected in the output Q. Okay, and then now the clock is changed to logic 1, that is, clock is enabled or control signal is enabled. Okay, so the output Q goes to logic high because the data D is logic high. Okay, here the data D is logic high. And then clock is disabled, here 0, so it maintains, Q maintains previous state value, that is logic 1. Okay, this logic 1 will be maintained. Right, even though the D is changed to 0. Okay, even though D is changed to 0 from logic 1, because of clock is disabled, output Q maintains the previous state value. Okay, here the logic 1 is maintained here also. Similarly, the another clock pulse. Okay, for the next clock pulse, data input is 0. Okay, and then clock is enabled. Then for this timing, the Q output goes to 0. Okay, when clock is, it maintains previous state value. Okay, 0 is repeated again. Okay, maintain up to this time. Okay, so like that waveform will go. Okay, so from these 2 examples, you can observe that for D flip-flop, if clock or control signal is disabled, there is no change in the Q output. It maintains previous state value. Once the clock is enabled or control signal is enabled, whatever may be the data available in D input, that will be applied to output Q. Okay, so this is the thing we can observe from D flip-flop. Okay, Hope you all understand the concept behind the D flip-flop, right? Okay. So then we will go for logic symbol. So here is the logic symbol. So D flip-flop having a single input, that is D. Okay. So along with the control signal, clock or enable signal. Okay, and produces two outputs, Q1, Q1. Okay. So this is the logic symbol used for circuit relationship. Okay. Then this is the functional table or logic table for D flip-flop. Okay, which is already explained. Whenever the clock signal or control signal is 0, irrespective of D input, output of Q will be does not change. Okay, it goes to memory state. Okay, when the clock signal is enabled, whatever the data available on the D, that will be applied to output Q. Okay. Then this is the characteristics table. So a characteristics table, we know that this table having present state, input, and next state. Okay. So for your understanding, you can observe like this. These two columns are assumed as inputs. Next state of this table is assumed as output. Okay. So present state Q, input D. Okay, if the present state value, right? Present state means previous output. Okay, if 0, okay, then if you are applying D equal to 0, the next state will be 0 because D flip-flop output will follows the input applied on the D input line. Okay, irrespective of present state value or previous outputs. Okay, that can be observed from this table. Okay, so present state value 0 here we are applying input 0 and 1. That data will be available on the next state value. Okay, even though the present state value is 1, if D is 0, that will be applied to next state value. Again, 1 is available on next state value. Okay, the next state value follows the input applied on the D input line. Okay, irrespective of present state or previous state values, previous output values. Okay, so next state values follows input. So this is the excitation table, right? So Q represents present state, Q of T plus 1 represents next state. So D is the input. Okay. So here we will determine the required input D based on the present state and next state values. Okay. That is the thing available in excitation table. Okay. So here the present state value is 0. Again, next state value is also 0. Right. So here you can say that both are same. Okay, so the state of flip-flop goes to memory state, or otherwise you can say the data available on D input is 0. Okay, now present state is 0, but next state is 1. If next state value is 1, what about the input applied on the data input like D? That should be 1. Because for D flip-flop, the next state value follows data available on data input D. Okay, so here also present state is 1, next state is 0. Because of next state 0, the required input is 0. Okay, so here also present state is 1, next state 1. Because of next state 1, the required input is 1. Okay, here also. So this is the excitation table, right? Then the third thing is characteristic equation. Okay, characteristic equation of D flip-flop. Okay, so the characteristic equation gives the Boolean expression for next state value, right? So from this table, characteristics table, you can observe that the next state value Q of T plus 1 follows D. Okay, Q of T plus 1 follows D, that is input. Okay, from this table also you can write the Boolean expression. Okay, Q plus or Q of T plus 1. Okay, that is equal to D. That is the characteristic equation of D flip-flop. Okay, so this is the characteristic equation of D flip-flop. Q of T plus 1 is equal to D. Okay, so from this you can observe that the D latch receives the name from its ability to hold data. Okay, ability to hold data which is applied in the input line. Okay, so whatever may be the data applied on the input line D, that will be available on the output. Okay, or it stores data, right? So it can be used as a temporary storage element, because whatever may be the input we are applying, that will be only available on the output line Q. Okay, so it is used as a storage element. The binary information present at the data input D is transferred to the output when control input is enabled. So this flip-flop is also called as transparent latch. Okay, transparent latch. That means this is the D flip-flop. Okay, so here I am applying data input D, and here I am taking the output key. So whenever the input clock control signal clock is enabled, okay, whatever may be the data applied on the input line D, that will be reflected in the output Q. Okay, so if you are applying 0 here, then you will get 0 on the output line Q. If you are applying logic 1 here, then you will get logic 1 here. Okay, when the clock or control signal is enabled. Okay, so input is directly available on the output. So because of this reason, this D flip-flop is also called as transparent latch. Okay. So any doubt in this D flip-flop? Any doubt? Okay. So we will move further. JK flip-flop. So JK flip-flop is designed for improving the SR flip-flop. Okay. So we observed the one drawback in SR flip-flop, that is when both the inputs are logic 1, then SR flip-flop produces invalid output. Okay. That means S equal to 1, R is equal to 1. This input combination is invalid for SR. Okay, so to avoid that condition, we are going for refinement of SR. Okay, that's why we have designed the D flip-flop, and then we are focusing on the another kind of flip-flop, JK flip-flop. Okay, so here we will use certain feedback mechanism. Okay, Q and Q bar both will be fed back to the input NAND gates, right? So, as I said, this flip-flop overcomes the indeterminate state of the SR flip-flop. Okay, when S equal to 1, R equal to 1, SR flip-flop produces invalid output. So, to overcome that problem, we are going for JK flip-flop, right? But the operation of JK flip-flop is similar to SR flip-flop. Okay, same as SR flip-flop. The difference is that JK flip-flop has no invalid output state. Okay, JK flip-flop has no invalid output state. That is the purpose of JK flip-flop, right? That's why we are designing the JK flip-flops. To avoid that invalid condition only, we are going for JK flip-flop from SR flip-flop. We are improving the SR flip-flop and designing JK flip-flop. Okay, with some modification. Okay. So when J equal to 1, K equal to 1, here JK represents inputs applied for JK flip-flop. Okay, in SR flip-flop, inputs are S and R. Similarly, in case of JK flip-flop, inputs are named as J and K. Okay, so when you are applying both the inputs are logic 1, j equal to 1 and k equal to 1. The next output is complement of the present. Okay, so when you are applying logic 1 on the each inputs, j equal to 1 and k equal to 1. Okay, for example, previous state values of q is 0, q bar is logic 1. Okay, so when you are applying j equal to 1 and k equal to 1, this q and q bar value will be complemented. Okay, so initially we have assumed q equal to 0, q bar equal to 1. Now, because of the input 1, 1, this data will be complemented. So q goes to logic 1, q bar goes to logic 0. Okay, so when you are applying logic 1 on both the inputs, output of q will be complement of the previous state values, previous state outputs. Okay. So this is the schematic of or logic diagram of JK flip-flop. Okay, level triggered JK flip-flop. Okay, so same structure, but the modification is here. You can observe that. Okay, so this is the input NAND gates. So 1, 2, 3, 4. Okay, the NAND gate 3 and 4 having feedback signal. So the Q is fed back to the NAND gate 4. Q bar is fed back to the NAND gate 3. Okay, Q is fed back to NAND gate 4. Q bar is fed back to NAND gate 3. Okay, so this is the modification available in JK flip-flop compared to SR flip-flop. Okay, and instead of S, we are having input J. Instead of R, we are having K. Okay, all other things are same. Right? So that's why we are saying that JK flip-flop act as SR flip-flop. Okay, without one modification. When you are applying logic 1 on both the inputs, output of JK flip-flop will be complement of previous state values. Okay, except these two differences, JK and SR both are same. Okay. So in level triggered JK flip-flop, the output is fed back to the input and therefore change in the output causes the change in inputs. Okay, so due to this feedback mechanism, in the positive half cycle, okay, positive half of the clock pulse, if J and K both are 1, then output toggles continuously. Okay, we are saying that both the inputs are logic 1, we will get complement of previous state value. Okay, this mechanism continues. Okay, if J and K having same logic, that is equal to 1, then output of JK flip-flop continuously toggles. Okay, toggling means 1, 0, 0, 1, 1, 0, 0, 1. And the continuous 1 and 0, 1 and 0, mari vandute. Okay, so this is continuous. Echo J and K values logic 1 la maintain. Okay, that is one limitation, you can say limitation, okay, of JK flip-flop. Okay, so this condition is nothing but race around condition. Okay, race around condition. Race around condition means race the Q and Q bar. Okay, both will try to win the race. That means both will try to get logic 1. Okay, if Q1 இருந்துச்சு Q bar 0 இருக்கும். அடுத்த டைம்ல என்ன ஆகும்? அடுத்த clock pulseல Q bar goes to logic 1, Q goes to logic 0. Then in next clock pulse, Q goes to logic 1, Q bar goes to logic 0. So this will happen continuously. Okay, this type of toggling happen continuously. Okay, so this condition is nothing but race around condition. Okay, so race around condition can be overcome by using edge-triggered flip-flop or master-slave configuration. Okay, so this race around condition in JK flip-flop can be overcome by using edge-triggered flip-flop or master-slave configuration. Right? So this is the schematic structure and function or logic table of JK flip-flop. So this is for understanding timing. Okay. So here you can understand the function of JK flip-flop. Okay, so initially I'm assuming 1, 0 on Q and Q bar outputs. Okay, so whenever the clock is disabled, both the NAND gates 3 and 4 having logic 0. Okay, so it will be logic 1. The output of 3 and 4 will be NAND gate 3 and 4 will be logic 1. If the input applied for this latch is 1 1, then Q and Q bar maintains its previous state value. There is no change. Okay, so Q0 will be maintained. Here you can observe the no change condition. Similarly, if the clock signal is enabled, if the clock or control signal is enabled, okay, here 1. Now, along with this control signal, see, I am applying 0 on both the inputs J and K. Okay, so because of 0 on input lines for NAND gate 3 and 4, here 0, here also 0. Okay, again this NAND gate produces logic 1, irrespective of this third input of 3 and 4 NAND gates. Okay, so again it goes to memory state. It maintains previous state outputs Q and Q bar. Okay, 1 and 0 will be maintained. Okay, again it goes to memory state. Okay, both this and the memory state. Okay, now input is changed to 0, 1. Okay, I am applying 0 on J, 1 on K. Okay, now what will happen? So now the previously assumed values are 1, 0. Okay, 1 on Q, 0 on Q bar. So this 1 will be fed back to NAND gate 4. Okay, here you can observe 1. Okay, because all the inputs are logic 1, the output of NAND gate 4 will be 0. Okay, but the output of NAND 3 is 1 because this input is 0 and also the third input is fed back from Q bar. This is also 0. Okay, so NAND gate 3 produces logic 1, NAND gate 4 produces logic 0. Okay, now NAND gate 1 having 1 on here, NAND gate 2 having 0 on here. Right? So NAND gate 1, the second input of NAND gate 1 is 0. Okay, then NAND gate 2 having output logic 1. Okay, so because of this kind of input, NAND gate 2 produces logic 1. Okay, so this logic 1 is applied to NAND gate 1. Okay, the NAND gate 1 having 1 1 on both the inputs, so this NAND gate produces 0. Okay, so for the input combination 0 1, Q goes to 0, Q bar goes to logic 1. So if the output Q is 0, that means reset condition. Okay, so this is the case. Okay, here you can observe reset condition. Right. Similarly, for the third input combination 1 0. So 1 0. Okay, so because of K equal to 1, irrespective of other two inputs, NAND gate 4 produces logic 1. Here, Q bar having logic 1, that will be applied to input of NAND gate 3. Okay, so for NAND gate 3, all the inputs are logic 1, so it goes to logic 0. Okay, so 0 1. For this input case, the latch produces set output condition. Okay, Q goes to 1, Q bar goes to 0. Right? So because of this data, okay, NAND gate 1 having 0 on 1 first input. So because of that, NAND gate 1 produces logic 1. Okay, that is applied to NAND gate 2. Okay, then here also logic 1. So NAND gate 2 having logic 1 on both the inputs, so it will be 0. So like that, output is changed to 1 0. Okay, this condition q is equal to 1, so this condition is nothing but set condition. Okay, then the third last possible combination is 1 1, right? So for the input combination 1 1, we are already discussed about the output of JK flip-flop will be complement of present state value. Okay, Q will be complemented as Q bar. Okay, so Q0 prime. Okay, so how it is possible? So you can observe from this table, from the structure. So here for NAND gate 4, clock inputs 1, K is 1. Then again this is comes from Q. So this is also 1 because of all the inputs are logic 1. Q NAND gate 4 produces logic 0. Okay, then for NAND gate 3, this is 1. This line is also 1, but this is coming from Q bar. Okay, that is 0. So it goes to 0. So because of one input is 0, NAND gate 3 produces logic 1. Okay, so NAND gate 3 produces logic 1, NAND gate 4 produces logic 0. Okay, so now this input is applied to NAND gate 1 and NAND gate 2. So this line having logic 1, this line having logic 0. So here logic 0. So because of this logic 0, irrespective of this input, NAND gate 2 produces logic 1. Okay, then this logic 1 is applied to NAND gate 1. Then again the output of NAND gate 1 goes to logic 0. Okay, so it is toggled. 1 complemented to 0, 0 complemented to 1. Again, I am retaining the input combination 1 1. Okay, and then I am applying next clock pulse on the control signal C. Right? So now the outputs are 0 1. Okay, same input is applied on the input J and K, and now applying next clock pulse. What will happen? Okay, same 1 1. The third input for NAND gate 4 is 0. Okay, now the Q value is 0. That 0 is applied here. Okay, 0 is applied here. Similarly, for NAND gate 3, clock 1, J1. What about this line? Q bar. Q bar is logic 1. So here logic 1 is available. Okay, so NAND gate 3 having logic 1 on 3 inputs. So output is 0. Okay, one of the input for NAND gate 4 is 0. So it goes to logic 1. It produces logic 1. Okay, now NAND gate 3 produces logic 0, NAND gate 4 produces logic 1. Okay, now this is applied to NAND gate 1 and so here 0, here 1. Okay, so consider this NAND gate 1. So one of the input is 0, so obviously it goes to logic 1 state. Okay, output of NAND gate 1 will be logic 1 because the first input for this NAND gate 1 is 0. So NAND gate 1 produces logic 1. This logic 1 is available to NAND gate 2 1 1. So this 1 1 produces logic 0. Okay, so you can observe from these two outputs. Okay, if I am maintaining the inputs 1 1, the outputs of JK flip-flop toggles, that is complements. Okay, 0 turn to 1, 1 turn to 0. Again, if you are assuming same condition, then it will goes to 0. This goes to 1. Okay, so like that it will toggles continuously. Okay, so this condition is but race around condition. Okay, so that can be observed from this timing diagram here. So this is my this table. These two conditions are memory state condition, no change, no change. So if Q goes to 0, that is reset. If Q goes to 1, that is set condition. If the output of previous state output complements, that condition is toggle condition, toggle state. Okay. So this is the timing diagram. So this is my clock signal. this is my input J, this is my input K. Okay, so previously we are assuming 0, output Q is 0. Okay, so if the clock is disabled or logic 0, Q maintains previous state value. Okay, that is up to clock when enabled. Okay, if clock is enabled, then Q will be depends on applied inputs. Okay, so during this time period, J equal to 1, K equal to 1. So output Q goes to logic 1. Okay, so when J equal to 1, K equal to 0, output Q will be 1. Okay, so this is the data here. Okay, so 1, 0, output is 1. Okay, so during this period, clock is disabled, so Q maintains previous state value. So 1 is maintained here also, irrespective of inputs. Irrespective of inputs. Okay, and then clock is enabled and Q follows the applied input. Now J is 0, K equal to 1. If J is 0, K equal to 1, what is the output Q? 0. So output is 0. Right? Then clock is disabled or logic 0. So irrespective of input variation, output Q maintains previous state value. Okay, so like that, this will be continued. Okay, whenever you are applying continuous clock cycle, right? So this is one example. So this is the another example. So from this example, you can observe the toggle condition or race condition. Okay, so same inputs C, J, K, and Q is the output. Okay, initially we are assuming Q equal to 0. So up to this time, clock is disabled or logic 0. So Q maintained previous state value. So now the clock is enabled. So the Q follows applied inputs. So J equal to 1, K equal to 0. Obviously, we know that Q goes to logic 1. Similarly, for the second input combination, still it is enabled. Okay, clock is enabled. So again, it follows input condition J equal to 0, K equal to 0. J equal to 0, K equal to both are 0, 0. If both the inputs J and K are 0, 0, it means that memory state. Okay, there is no change in the output Q. So still it maintains previous state value. Okay, logic 1 will be followed here also. And then both the inputs are logic. Okay, still clock is enabled. Both the input J and K both are enabled. Then you will get the output like this. Okay, toggling condition. What will happen? Initially 1 is complemented 0, and then 0 complemented to 1, 1 complemented 0, then 1, 0, 1, 0, like that. This toggling condition, complement function is continuous. Okay, so this condition is nothing but race condition. Okay, so Q is trying to make its line to logic 1. Okay, Q always trying to stable at logic 1, but because of the applied input J equal to 1 and K equal to 1, it varies. Okay, 1, 0, 1, 0 like that. Okay, so it will be continued up to the input J and K are 1, 1, or the C clock input is disabled. Okay, so once the clock is disabled, then it goes to previous state value. Okay, under this time output is 1. After that, C goes to 0. So Q follows next previous state value 1. Okay. So this condition is race around condition. So this is the logic table for JK flip-flop. Okay, so these things are already discussed in the circuit itself. Okay, so just to recall the things. So when clock is disabled, logic 0, irrespective of inputs J and K, output of JK flip-flop will be memory state. Okay, it retains in memory state. Okay, when the clock is enabled and both the inputs are 0, 0, again it is still in memory state. There is no change in the output. Okay, then if you are applying JK equal to 0, 1, then it goes to reset condition, because K value is 1, so it goes to reset condition. So Q value will be 0. If you are applying input combination 1, 0, then Q will be logic 1. it goes to set condition. When both are logic 1, it goes to raise around condition. Okay, so continuously output of JK flip-flop will be output. Okay, so this is the characteristics table. So this characteristics table takes both inputs and present state outputs. Okay, so Q, J, K. Right? So here the present state value is 0, inputs are 0, 0. That means memory state. Memory state means output of JK flip-flop follows previous state output or present state output Q. Okay, that Q will be followed here. Okay, then JK is applied with 0, 1, it is reset condition. Present state is 0, then next state value is also 0 because reset condition. Okay, so 1, 0, it means set condition. Present state output is 0 here, but the next state value is 1 because J equal to 1, set condition. When present state value is 0, when you are applying both the inputs are 1, 1, then it goes to complement of the present state value. Present state value is 0, so it is complemented to logic 1. Okay, then for logic 1 condition, okay, same operation will be followed here. 0, 0 means memory state, it follows present state output to next state. Okay, 1 repeated in the next state. Okay, 0, 1 is the reset condition, so 1 reset to 0. Okay, 1, 0 is the set condition, so 1 set to logic 1. Okay, 1, 1 means toggling condition. So if logic 1 is available in the present state, that will be complemented on the next state. Okay, 1 complement to 0. Okay, so this is the characteristic table, right? Then this is the excitation table. So excitation table gives the possible inputs required for JK flip-flop to get predefined in present state and next state values. Okay, so Q0, Q of t plus 1, present state, next state, both are 0, 0. That means two possibilities. One is memory state. Okay, so because of next state 0, it is also possible for reset condition. Okay, so memory state means both the inputs are 0, 0. Reset condition means J equal to 1, K equal to 1. Okay, so J value retained is 0. So here we are taking 0, but J varies from 0 and 1. Okay, so we are assuming as don't care condition. Similarly, for Q equal to 0 and Q of t plus 1, logic 1, it means that set condition. Present state value is 0, but next state value logic 1. Right? It means that set condition. Okay, or complement condition, toggle condition, set condition, or complement or toggling condition. Okay, because 0 is complemented to 1, right? Complement or toggle condition. Okay, so if it is set condition, you can say that J equal to 1, K equal to 0. If it is toggle condition, J and K both will be logic. Okay, still J maintains same value, but K maintains variable 0 and 1. So here also we are taking don't care condition. Okay, then here present state value is 1, next state value is 0. Here also two conditions. One is 1 complemented to 0, that is toggle condition. Another one is 1 reset to 0, so reset condition. Right? So toggle condition means both will be 1, 1. Reset condition means J0, K value is 1. Right? So J is the 1 and 0, don't care condition. K value is 1. Okay? So when you are applying this kind of input, then you will get Q equal to 1. For that value, next state value will be 1. Right? Then present state value 1 is maintained in next state value. So here also two possible conditions. One is memory state, because next state value maintains present state value, and another possibility is set condition. Okay, next state value is 1, so the possibility for another condition is set condition. So memory state and set condition. So memory state means both should be 0, 0. Set condition means J should be 1. So J is plus don't care, K value is 0. Okay, so this is the excitation table for JK flip-flop. Okay, then to derive the characteristic equation of JK flip-flop, okay, we need to analyze the characteristics table. Okay, so in characteristics table we will list three variables J, K and Q, right? So J, K, Q, present state values. Okay, so if inputs are 0, 0, then next state will be, what will be? Present state values, because no change condition or memory state condition, right? So Q of t will be followed in the Q of t plus 1, that is memory state or no change condition. Okay, then for the next possible inputs 0, 1, it means that reset condition for both the input combination, whatever may be the present state, next state will be 0, 0, right? That is reset condition. Third possibility 1, 0. For this input combination, next state value will be set, because J equal to 1, K equal to 0. Okay, then whatever may be the present state value, that will be logic 1 in the next state value, that is set condition. Okay, when the inputs, both inputs J and K are 1, 1, then present state value will be complemented, that is toggle condition. If present state value is 0, that will be complemented to 1. If present state value is 1, that will be complemented to 0 in the next state. Okay, so based on this characteristics table, we will find the characteristic equation. Okay, so this is the characteristics table. Here we can have a 3 variable KMAP. So H is, okay. So here we can take the J, K, Q. Okay, so min term here 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 1, the table here also, you know the things. Okay, 4, 5, 7, 6. Okay, so cells 1, 4, 5, 6. Okay, 1, 4, 5, 6. Okay, all are filled with 1, other cells are filled with 0. Okay, there is no need to fill the zeros. Okay, anyway, for understanding here in this KMAP, 0 is filled. Okay, it is not mandatory. Okay, after filling the number of ones, you can group the number of ones, okay, with the maximum possible number of ones, and you can get min terms. Okay, so here this is one possible. These two ones are grouped. Here you can assume that 0, 1, right? Here J value is 0, 1, right? 0, 0. Here 1, 1, then 1, 0, right? So this group gives K bar Q. K bar Q. Okay, the second group. Okay, the second group gives J, then common term is Q. From here, J, Q bar. Okay, by summing these two min terms, then you will get Boolean expression for next state value. Okay, Q of t plus 1 is equal to J Q bar plus K bar Q. So this is the characteristic equation for JK. Okay, so J Q bar plus K bar Q, or you can say J Q prime plus K prime Q, right? Any doubt? Any doubt? Okay, so next we will start with the fourth flip-flop, T flip-flop. Okay, so T stands for toggle. Okay, so this T flip-flop is designed to overcome the limitation of JK flip-flop. So for the fourth combination of input 1, 1, J equal to 1, K equal to 1, JK flip-flop toggles continuously, right? So to avoid that condition, we are going for T flip-flop. Okay, so level triggered T flip-flop. So T stands for toggle, or you can say toggle flip-flop. D flip-flop stands for data flip-flop. Okay, so T flip-flop is obtained from JK flip-flop by tying both the inputs together. Okay, so J and K both are tied and provides single input. Okay, that is T. The name T comes from the ability of the flip-flop to toggle or complement its state. Right? So regardless of the present state, the flip-flop complements its output when T equal to 1. Okay, so when you are applying T equal to 1, that 1 will be applied on both the input J and K. Then what will happen? Continuously toggles its outputs. Okay, when T equal to 0, then output goes to memory state. Right? So two possibilities. When you are applying both J and K gets 0, 0, then flip-flop goes to memory state. When you are applying T equal to 1, then it goes to toggle state, that is complement condition. Okay, the previous state output is continuously toggles, continuously complements, right? So this is the schematic structure or logic diagram of T flip-flop. Okay, there is only one difference. Okay, instead of having two input J and K, okay, J and K, okay, here we are tying these two inputs and providing single input. Right? Other things are same. Okay? So circuit operations also similar to JK flip-flop. Right? When T equal to 1, when clock is disabled, definitely it goes to memory state. Right? Irrespective of the input applied on the T. Okay? When input is, that is, clock is enabled by logic 1, then if you are applying logic 0 on the input line T, then J and K gets 0, 0. Okay, if input J and K are both 0, 0, again it is in memory state. Okay, if you are applying logic 1, what will happen? Both J and K gets logic 1. Okay, if both the inputs are logic 1, J and K are logic 1, then it goes to toggle state. Okay, so only two possible states, memory state and toggle states. Okay. So this is the logic table. When clock is or control signal is disabled, irrespective of the input applied on the input line T, the state of T flip-flop will be memory state. Okay. Then if the clock is enabled, if T equal to 0, again is still in memory state. T value is 0, it goes to raise 7 condition or toggle condition. Okay. This is the logic table for T flip-flop. Then characteristic table. Again, here we will consider present state and the inputs. Based on these two data, we will determine the next state. Okay, so here the present state value is 0. The applied input is 0. T is also 0. Present state 0. Applied input also 0. When the T value is 0, output of flip-flop is no change. That is memory state, right? So the present state value is maintained in the next state value. When T equal to 1, what will happen? Raise surrender condition, that is toggling condition. The present state value 0 is complement to 1. Okay. Then again, if present state value is 1, but T value is 0, because of T value is 0, flip-flop goes to memory state, so it maintains present state value. When T equal to 1, it goes to toggle condition, 1 is complement to 0. Okay, so this is the characteristics table for next state. Characteristics table for T flip-flop. Right? So this is the excitation table. Here also same condition. Input present state value is 0, next state value is 0. So it is memory state. So to provide a memory state, T should be 0. Okay, input P should be 0. Right? T equal to 0, but next state is 1. 0 complement to 1, that is toggle condition. To enable toggle condition, T should be logic 1. Similarly, present state is 1, next state is 0. 1 complement to 0. So again toggle condition, T should be 0. Here Q equal to 1, that will be maintained in the next state, so memory state, so T should be 0, right? Then the characteristic equation, T Q bar plus Q T bar. How? From this table, characteristic equation. Okay, so if you are seeing this truth table, okay, this characteristic table, it is very similar to XOR gate. Okay, if both the inputs are same, then output of XOR will be 0. If both the inputs are opposite or not equal, then output of XOR will be logical. Okay, it follows XOR gate. Okay, the output Q of T plus 1 follows XOR gate. That's why we are directly writing like this T, because input for this column Q of T plus 1 is Q and T and Q. Okay, so inputs T XOR with Q gives next state value Q of T plus 1. Okay, that's why we are directly taking characteristic equation. Or otherwise, you can draw a K map, fill the number of ones, map, then you will get minterms. Summing the minterms will give final Boolean expression for Q of T plus 1. Okay, the characteristic equation for T. Okay. Any doubt? Any doubt in this T flip-flop? So T flip is very simple concept. If you understood the JK flip-flop, then you can easily understand the T flip-flop. Okay, because both are almost same. Among 4 possible conditions, T flip-flop having 2 conditions from JK flip-flop. Okay. Then the next type of flip-flop is edge-triggered flip-flop. So still now we have discussed level-triggered flip-flop. Okay. So based on the level-triggered mechanism, we have discussed 4 different flip-flops. Okay. SR, D, JK, and T. Okay. Now we are going to just overview on edge-triggered flip-flop. Okay. We are not focusing on this particular topic. Okay, so we are going to just incur concept behind this edge-triggered flip-flop. Okay, so for example, here we are taking D flip-flop. Okay, with the help of D flip-flop only, we are going to explain the concept behind the edge-triggered flip-flop. Okay, so an edge-triggered D flip-flop can be constructed by employing 2 latches. Okay, it having 2 states. Okay, in each stage we will use 1 flip-flop or latch. Okay, so edge-triggered flip-flop can be constructed by employing 2 latches in this special configuration that isolates the output of the flip-flop and prevents it from being affected while the input to the flip-flop is changed. Okay, so here we are using special configuration, that is master-slave configuration. Okay, so in master-slave configuration, we will use 2 latches in cascade mode. Okay, so in 2 latches we will apply same clock signal or complement clock signal. Okay, the first stage is applied with the true form of clock signal. The next stage is complement of the clock signal. That means first stage receives clock 1, then obviously next stage receives clock 0. By using NOT gate, we will complement the clock signal to next stage. Okay, the first stage is named as master stage. Second stage is named as slave stage. Okay, so with the help of this configuration, we will construct the edge-triggered flip-flop. Okay, so this is the structure of edge-triggered flip-flop, or you can say master-slave D flip-flop. Okay, so here we are having 2 stages. This is the stage 1 called master stage, stage 2 called slave stage. Okay, master-slave D flip-flop. Okay, in both the stages we are using D latch. Right? So D input, clock input, Q output. D input, clock input, Q output. Okay? So the master stage is controlled by clock signal, that is true form of clock signal, that is clock is directly applied to master stage. but slave stage having complement of clock signal. Okay, with the help of this NOT gate, we are complementing the clock signal. Okay, that means either one of the stage, okay, will be active at a time, right? If master stage is active, slave is inactive. If master is inactive, slave is active. Okay, so based on this concept, we are constructing the H-triggered flip-flop, right? So this is the time diagram used for understanding the concept behind the H-triggered flip-flop. Okay, so here we are taking clock, then the applied input D. Okay, then here Q master, Q slave. Q master means here, this line. Okay, so this is the Q master output, this is the Q slave output, right? So this is the this is actual output, but here slave, here master. But actual output of master slave D flip-flop is slave. Okay, so now come to the time diagram. We know the concept of D latch. Okay, whenever clock is disabled, then output of D will be previous state. Whenever clock is enabled, then Q follows D output. D input. Okay, same thing is applied here. Okay, for master. When the master is active, how we are enabling the master? Because here the clock signal is logic high. This logic high is applied to master stage. Okay, here the clock is high. Okay, this high input is applied to master, but the clock is inverted as 0. Okay, then slave is inactive. Okay, so D latch in master stage produces output. Okay, so when clock is enabled, Q master follows applied input. Okay, master is applied with data input D. Okay, so if data goes to 1 and clock is 1, Q goes to 1. Okay, if data D goes to 0, output also goes to 0. Okay, this is for again D goes to logic 1, again Q master goes to logic 1. Okay, so this will happen up to clock is high. Okay, once the clock is disabled, that is it goes to logic 0, then Q master will be disabled because clock is 0. Okay, so D master stage is disabled, then output of this master stage will be previous state output. Okay, it goes to memory state, it maintains logic 1. Right? It means that the input applied on this input line data D is now available on the Q master line. Okay, now the input D1 is transferred to Q master line here. Okay, data is transferred to this line. Right? Now the clock is 0, so because of 0, master stage is disabled. Now slave is enabled because inverter of clock. Okay, now slave is enabled. Okay, so for this output will be like this. Okay, so for clock 1, slave stage is disabled, so it maintains previous state. When clock goes to 0, slave state is enabled by this NOT gate. So output of Q slave is logic 1. Right? Because input for this slave stage is Q master. Okay, so this is the input for slave. Okay, this is the input for slave output. Okay, so this is input, this is output. This input for slave stage is fixed at logic 1. So output of Q slave is also fixed at logic 1. Okay, so you can also say that the slave operates when you are applying low logic clock cycle, that is negative cycle. Okay, so it looks like negative H triggered. Okay, negative H triggered flip flop. Okay, so this is the concept behind the edge-triggered flip-flop. Okay, like that you can construct different flip-flops. Okay, JK flip-flop, D flip-flop, T flip-flop, SR flip-flops. Right? Then you can recall the things. So the logic table, logic diagram used for SR flip-flop. Okay, so SR flip-flop having two inputs S and R with clock signal and two outputs Q and Q bar. Complement outputs. Okay, then this is the logic diagram. So logic table. 0, 0. When you are applying 0, 0, then output goes to memory state. Then when you are applying 0, 1, it goes to reset state. When you are applying 1, 0, it goes to set state. When you are applying both 1, 1, it goes to indeterminate state, that is invalid state. Okay, then D flip flop. Right, so D flip flop having single input along with the clock signal, then two outputs Q and Q bar. Right, so output Q follows input D. Right, so whatever may be the input applied, that will be available on the output line Q when clock is enabled. Okay, that is the mean condition. Then JK flip flop. Here also two input J and K, one control signal or clock signal, two outputs Q and Q bar. When you are applying 0, 0 inputs, it goes to memory state. When you are applying 0, 1, reset condition, 1, 0, set condition, 1, 1, toggle condition. Right? So T flip flop, single input T along with control signal or clock signal, two outputs. Here, when you are applying T equal to 1, then flip flop goes to memory state. When you are applying T equal to 1, sorry, T equal to 0, it goes to memory state. T equal to 1, it goes to toggle state. Okay, the condition is that for all the four flip flops, clock signals should be enabled. Then only you can observe this kind of outputs. Okay, then negative edge triggered flip flops. Okay, still now we will discuss positive edge triggered flip flop. Okay, so no difference, but the thing is, still now we have discussed positive edge triggered. So here, true form of clock signal is applied, right? But here we are having complement. This bubble denotes complement form of inverted form of clock signal. Okay, rest of the operation is same as positive edge triggered flip flop. Okay, so positive edge triggered flip flop operates when you are applying positive level. Negative edge triggered flip flop operates under negative cycle of the clock signal. Okay, so logic diagram will be like this. Logic symbol. Okay, logic symbols of JK flip flops. So here the clock signal will be used one bubble. This bubble represents negative edge trigger. Okay, these are the excitation tables of SR, D, and JK and T flip flops. Okay, just recall the things. So hope all of you understand the concept behind the D flip flop, JK flip flop, and T flip flop. If you have any doubt, you can ask me. So in this session, we have discussed three flip flops: a D flip flop, JK flip flop, and T flip flop. Okay, and also we have seen the concept of edge triggered flip flop. Okay, so for example, we have taken D flip flop and we have constructed edge trigger flip flop in master slave configuration. Right? Any doubt? So in the next session, we will see how to realize the one type of flip flop from another type of flip flop. Okay, so it is possible to construct JK flip flop using D flip flop, T flip flop using D flip flop. Okay, JK flip flop using SR flip flop, like that. Okay, one type of flip flop can be realized from another type of flip flop. Okay, so that will be discussed in next session.
Sir.